This last video for Chapter 13 is probably the most important both when it comes to the AP exam as well as the SAT subject exam in physics, okay? Kepler orbits, okay, so these are the actual orbits of the planets in our solar system and all across the universe. There's three main things that you need to know about Kepler orbits. Number one, all planets move in elliptical orbits. So we've got the sun. Every planet does not orbit in a perfect circle. It is actually more of an elliptical pattern. I'm obviously doing a very exaggerated one right now, but all the planets orbit some central focus, in this case the sun, in an elliptical pattern. The second one is a little weird. It's known as the law of areas, but that allows us to do something very neat up here with the law of periods. So if this one doesn't make sense, it's going to be used up here on the law of periods. The law of areas. Okay, so here let's say I've got the Earth, and it's moving around the sun right here. And again, I've made the elliptical orbit very exaggerated, but bear with me, okay? Let's say we record an amount of time, okay? Like 1 month. And in 1 month, the Earth goes from here to here. Okay, in 1 month, the Earth goes from there to there. We can trace out the area covered by the Earth during that 1 month period, and let's call that area 1. Okay? Now we're going to let the Earth get all the way over here, and we're going to record a second month. And in that second month, the Earth goes from here to here. And we're going to trace out that area right here. We're going to call this area 2. If we record the exact same amount of time, the area that's cut out by the Earth during that orbit is going to be the same. So area 1 is going to be equal to area 2. Now there's a lot of implications here. The first implication, it should be fairly obvious that the Earth is going to have more velocity. It's going to be moving faster when it's closer to the sun. Go back to our previous energy conservation talk. The potential energy is going to decrease as the Earth gets closer to the sun, so the kinetic energy is going to increase. That's the first implication. So the object is moving faster the closer it is to the sun. If you've ever seen the movie Apollo 13, this is how they actually built up kinetic energy as they went around the moon in order to get back home. Maybe we'll watch that movie if we come back at the end of the school year, okay? The more important thing is that this allows us to use the law of periods. This allows us to analyze the periodic motion of a planet orbiting something in the same way that we did for centripetal force, okay? So we remind ourselves that the force of gravity equation is big G m1 m2 over r squared, okay? We're going to rewrite that as big G m over r squared to indicate the big mass that we're orbiting around, the little mass that is doing the orbiting, okay? If this is the only force on our object, then this must be equal to the centripetal force that is keeping us in uniform circular motion. Now at this point, somebody's going to ask, well, wait a minute, you're moving around in an elliptical pattern. How can you say that you're moving around with a centripetal force in uniform circular motion? The law of areas is what allows us to do that. Because the law of areas holds true for any amount of time, I can sort of formulate this thing as a uniform circular motion problem, and I can solve for the period of the motion. Before I go through and actually do that, let me tell you right now, this is probably the #1 question on the AP test. I don't know why. They love this derivation for the force of gravity to the centripetal force to the period of the motion. And time again, it's like free points. They ask you to do the derivation for an object that is in some kind of elliptical orbit. So I would actually recommend knowing this proof. I'm not going to ask you to do it on a test, but knowing how to do it, it's very easy, 1, and 2, it comes up over and over again on the AP. Okay? So force of gravity is equal to big G, big M, little m over r squared. That's equal to our centripetal force. And so we're going to say that big G, big M, little m over r squared is equal to little m v squared over r. Okay? So I'm replacing the centripetal force with mv squared over r, mass multiplied by the centripetal acceleration. Okay? We're going to manipulate this thing a little bit and we're going to transform this into m omega squared times r. So I'm using from the previous chapters v is equal to r times omega. I've got r times omega squared, one of the r's cancels, and now I've got m omega squared times r. We then remind ourselves that the period of the motion is 2 pi over omega, 2 pi over the angular velocity. And so now what I'm going to have here is, I gotta remember how exactly I want to do this. Probably should have looked at it before I started doing this, but what the heck, we can go ahead and do it. I need to get 2 pi, if I solve for omega up here, if I solve for omega up here and then plug it down in here, I should get a period equation that I like. So let's solve for omega up there. Omega is equal to, little m's cancel out. Looks like this r would go down here and it becomes an r cubed down in the denominator. That looks good. So then I'm going to have omega squared is big G, big M over r cubed. Okay? So what I did was I solved for omega squared up there. I got big G M over r cubed. Okay? That looks nice. If I were to take the square root of that, we would kind of have a little bit of a mess. So we don't want to do that. What we instead want to do is we want to take this period equation and let's make it period squared is equal to 4 pi squared divided by omega squared. So all I did was square everything. Now I'm going to caution you guys real quick. What I did here was I did 2 pi the quantity squared to make 4 pi squared. This is one of the easiest things students screw up whenever they plug it into their calculator. They end up plugging in 4 pi, the quantity squared, instead of 4 times pi squared. I always take a look at this whenever I use it in my calculator. Pi squared is going to be a little bit more than 9. A little bit more than 9 multiplied by 4 is a little bit more than 36. So you should have something that's a little bit more than 36. Make sure you always plug that in first. Now I'm going to plug the omega squared down here into the t squared, and I'm going to have that t squared is equal to 4 pi squared divided by, this is now big G M over r cubed. Okay, looks like I did it right. We want to make this look a little bit nicer, so let's bring the r cubed in the denominator down there up top to the numerator. And I've got t squared is equal to 4 pi squared r cubed over big G M. This is the derivation that they look for over and over again. The period squared is equal to 4 pi squared r cubed divided by big G, mass of the object that we are moving around. They love this derivation. What they're relating is that the radius cubed is proportional to the period squared. That is what they are interested in. This is known as the law of periods, that the period squared is proportional to r cubed. This is a derivation, again, that I will not ask you guys to do, but it is a derivation that you should know because it will probably come up on the AP exam where they directly ask you guys to do it.